Yeah, hello. So is the screen visible to all of you? Okay, thanks. So we'll start. So in the last class, we saw what a vector space is. We saw some of the examples of it. Particularly, we saw the example of Rn. Then I also mentioned some more examples, some examples on functions, if I correctly remember. So I will just check the examples that I mentioned. Yeah, so I gave the example of matrices, then functions. Yeah, so today we'll start with looking at vector additions. Okay, so what do we actually mean by vector additions? Okay, so let's talk about R2. Okay, so in R2, what is vector addition, or what is the geometrical interpretation of the vector addition? So see, we know what do we mean when we say we are adding two numbers, right? So example, let's say this is the line R, this is my real line, this is 0. Okay, this is this. I know if I have a number 1 here, and if I have a number 2 here, and if I add them, so what do I get? I move to the right side of the line, that is I get this 3. This is 1 plus 2. So geometrically, whenever we are adding two real numbers, what we are doing actually, we are moving towards the right side. Similarly, when we subtract something, so if I subtract, let's say minus 1, so if I do 2 minus 1, so what I'll do, if I minus something, I move to the left hand side. So if I do minus 1 from 2, so I'll get this, I'll be here, this is 2 minus 1. So in R, we understand, right, that adding two things means something, that we have some geometrical interpretation, we have some geometrical meaning to it. But what happens when we are adding two things in a R2, or we are adding two vectors? So in R2, we do not have real numbers, right? We have vectors, we have ordered pairs, right? We have some point x1 comma x2 here. Okay, and we have some point y1 comma y2 here. Let's call it a, let's call it b. So what do we mean by a plus b in R2? This is the question, right? So in the real number system in R, we understood that okay, we have the line, we can move towards the right, we can move towards the left. But what do we actually mean when we say that we are going to add two vectors in R2, right? So this is what we'll discuss first. So let's say, again I'll just draw the picture here for the sake of completion. Let's say I have the point x1 x2 here, and I have a point b of y1 y2 here. Okay, so what is a plus b? Call a plus b equals c. And what is this c? C is nothing but x1 plus y1 comma x2 plus y2, right? But how do we get it? So assume that this is the position vector of a, this is the position vector for b. Okay, And then what we do to get C, actually we make a parallelogram, right? What we do is that we make a parallelogram. So this is what a parallelogram will look like. Okay, and this point is C, which is my x1 plus y1 comma x2 plus y2. So in R2, whenever we are adding two vectors, okay, so how do we add it, or what does it mean geometrically? That actually this is the, we add it through the parallelogram law. That is, we take A, we take B, we take the position vectors, that is these lines, this line and this line, and what we do, from these two lines we make a parallelogram. Okay, and so this is the parallelogram I made, and this corner point, or this point of this parallelogram, this we call it as C. Okay, and this is what essentially we mean by adding two vectors in R, in R2, not Rn, sorry. So in R2 we are using parallelogram, right? What happens in R3? So obviously, since this is a 2D plane, we cannot uh, visualize, or we cannot write how a vector in R3 would look like. But how do we add in R3? Okay, so in R2 you use parallelogram law. So in R3, what we will use? We will use parallelopiped, right? So we know that in R2 we have a square, and in R3 that square becomes a cube, right? Similarly, in R2 we have parallelogram, okay, and in R3 it becomes a parallelopiped. So the same thing will happen in R3, in R4, and R5. Okay, and what will happen? Only this extension of this parallelogram law will be done. So in R3 we will be using a parallelopiped, and similarly. Okay, so this was the first thing. Yeah, so we saw what a vector space is in the previous class. Now what we are going to see, what a subspace is. Vector subspace. So earlier also you had, first you define groups, okay. Then what you did is that you 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 had taken a subset of that set, okay, and you check that if this set satisfies all those properties that my original set was satisfying, I'll call it a subgroup. And similarly, here also we will do the same thing, that first we will take a vector space, we will take a subset out of it, and we will check that if all these properties are satisfied or not. If all the properties are satisfied, we will call it as a vector subspace. So yeah, actually, okay, I'm having some problem with this. Let me just, yeah, so is my screen visible and my audio is like proper?
Yes, sir.
Okay, fine, thank you. So we will define what a vector subspace is, but okay, so before actually we formally define what a vector subspace, I just want to give one or two more examples. Okay, so let me call it as example 1 here for this class. And so I'm going to give some more example of the vector space that we saw in the last class. So in this example, I'm taking the vector space of the set of all sequence. So you have studied sequence and series, and you know what a sequence is. So let V is the set of all real sequence. Okay. Then this V over R is a vector space. Under the operations, xn plus yn is equals to xn plus yn. So basically what we'll do, we will just add the sequence component wise and nothing else, and alpha of xn is alpha xn, that is again component wise. So these are component wise. So in a sequence you have x1, x2, x3, x4 terms go on like this. So if you have x1, so you need to add x1 to y1, x2 to y2, x3 to y3, and like that. Okay, so this is one example which is a vector space. So okay, so you guys should actually check all the properties. So I'm not going to check all the properties here, because it is, if you guys try it, it is very easy. And yeah, so the zero vector is what? The zero sequence, all the elements would be 0. And for any sequence xn which has the form this a1, a2, an, what would be the xn inverse? So xn inverse, which we denote as minus of xn, is nothing but minus of a1, minus of a2 to minus of an, right? So this is just for your understanding. So this is one example in which I have taken all the sequences, all the real sequences. Now again I'll consider one more example, and I'm going to take this time as the set of all polynomials of degree at most n. Okay, and with respect to our usual polynomial addition, scalar multiplication. So we know how to add two polynomials, right? And we know how to multiply a scalar to a polynomial. So if we have two polynomials p1 and p2, all we have to do is that we have to see the coefficients corresponding to the same variables, and we add or subtract them. And for scalar multiplications, we just multiply all the coefficients by that scalar. So this is something you already know. Okay, and this is also a vector space. Then one more example we can see. So it is a vector space, means it will satisfy all the properties. Okay, it satisfies all the properties. So for a polynomial function, what is going to be my zero element? Obviously the zero polynomial in which all the variables have the coefficient 0. And for any polynomial p1, let's say if it has the form a1 x1 plus a2 x square a3, so let me just write it actually. So the zero element is nothing but the zero polynomial, right? And for any polynomial p1 which has the form a1 x1 a2 x2 up to an xn. Okay, so this is not x2 actually, this is x square, and this is my x power n. Okay, so if the polynomial has degree n, it means the highest coefficient we can go, highest variable we can go is x power n. So what is going to be minus of p1, or what is the inverse? It's simple, obviously minus a1 minus a2 x square and minus an xn, right? So this is again for your understanding. Now one more example I'll take. This time I'll take v as the set of all functions. okay, and these functions are defined from R to R, okay, and f is continuous. So basically what we are taking a set V which has all the continuous functions whose domain is R and whose range is also, or whose codomain set is also R. So all the constant functions, all the polynomials, all your trigonometric functions, sin x, tan x, okay, all those functions that are continuous over R, obviously. So tan x may not be continuous over the whole R, but sin x is. And similarly, exponential function or whatever, all those functions which are continuous over R that we are going to define. We are taking the set as V, and we define that f plus g of x. So basically we take two functions, one function is f and one function is g, and now we want to add the two functions. So how are we going to define that? Nothing but just I'll take the function value at x of the first function, and then I'll take the function value of at x of the second function, and I'll add these two. And similarly for scalar multiplication also. So what I'll do is that first I'll find out the value of the function at that point x, and then I'll multiply it by scalar. So this is the our usual way in which we add or subtract or multiply two functions. Okay, so this is again a vector space. Again, the zero function or the function which takes the value 0 is going to be my zero element, and for any fx, minus of fx will be my inverse, right? So yeah, so with these examples actually now we can go and formally try to define what a vector subspace is. Okay, so I gave these examples because we will use these examples to understand the concept of vector subspaces. So what is a vector subspace? Yeah, so till here, if you guys have any doubts, you can write it in the chat box if you guys have any doubt. Okay, fine. So to define a subspace, what we used to do is that we used to uh, little molia. Okay, I think you need to switch off your TV, I guess, or at least your mic. Yeah, thanks. Yeah, so vector subspace. So let V be a vector space and W be a subset of V. Okay, so we say W is a subspace or a vector subspace of V if, now there are certain conditions that we need to check. Number one is that first W should be non-empty. Okay, so you cannot define any operation on an empty set. So the first condition should be that it must be non-empty. That means it must have at least some element, at least one element. And the number two is W itself is a vector space. under the same operations. Now, what do we actually mean by this under the same operations term? What it actually means is that, whenever we define a vector space, so we define some kind of addition and some kind of multiplication on it, right? So when we define a vector subspace, the same definition should be applied. So it cannot happen that we can apply some different definition of plus or some different definition of scalar multiplication on the subset, and on the whole vector space we define it differently. So this won't work. So the operations must be same. Okay, under the same operations from V, and that is to say, so see, either when I say W itself is a vector space, it means W will have to satisfy all those eight or 9 points that we discussed in the first class, right? But actually the good thing is that we do not have to check all those criterias. Rather, we can just check 3 of them. So the first one is that the 0 element should belongs to my W. The second one is that if W1 plus W2 belongs to my capital W, then that implies W1 plus W2 belongs to capital W. It means what? It means closure with respect to addition. What does it mean? That if I take any 2 elements of the set W and if I add them, or if I apply the operation plus on them, the result should again be in the set itself, in the set W itself. That is my second condition. And the third condition is similar, that for alpha belongs to R and my W belongs to W, the scalar multiplication, that is alpha W, this also should be in W itself. Means closure with respect to scalar multiplication. So if any set, okay, or any subset of the vector space V, if it satisfies these 3 properties, we will say that okay, this set is actually a vector subspace. The benefit is that we do not actually have to check now all those 8 properties for vector subspace. So now to make this clear, actually we will see some examples. So example 1, okay, so let V I am taking as R3, okay, R3 over R, and I take a subset of V, okay, which take the elements of this form x, y, 0 such that x comma y belongs to R. So clearly we can see that W is a subset of R3. Clearly all the elements are W are in R3, okay. Then this W is a vector subspace. Okay, so actually how do we check it? So like I should write not then, I should write is. So this is a question. So is W a vector space of R3 or not? So again, to check whether something is a subspace or not, we need to check 2 things. First, that it should be non-empty. So clearly we can see that W is non-empty here, right? Because it has the element at least 1 comma 1 comma 0 or 0 comma 0 comma 0 is there in W. So it is not empty. That is fine. Then I have to check that if this W is actually following these 3 properties or not, that we have just written above. So let us check. So 1, so clearly 0 0 0 belongs to W, that implies that my 0 vector belongs to W. So the first condition or the first check is okay. So the first condition that I had to check, that the 0 belongs to W, it is fine. Now what about the second one? That is closure with respect to the plus addition. So now if I take any two elements, W1, let me call it as x1, y1 0, and W2, okay, which is x2, y2 0. So what about W1 plus W2? What is this? So this is x1 plus, sorry, this is x1 plus x2, y1 plus y2, comma 0 plus 0, which is my sum z1, z2, comma 0, and this again belongs to W. Means what? I took any two arbitrary elements of the set W, I called them as W1 and W2, I took their sum, and I found that okay, they also belongs to the set itself. So the second condition or the second criteria is also fulfilled. Now what about the third one? That is closure with respect to scalar multiplication. So what happens here? So again, if I have some element W1 which is of the form x1, y1, comma 0, and let me take any element alpha that is in R. What is my alpha W1? Alpha W1 is nothing but alpha x1, alpha y1, comma alpha times 0 is again 0, and this is again sum z1, comma z2, comma 0, and this also belongs to my W, right? Means it is closed under scalar multiplication as well. So I took any arbitrary element of W, I multiplied with some scalar alpha, and I found out that okay, this element was again found in the set W itself. So all the three properties, all the three things that we have to check are satisfied. So we will say that okay, the answer is yes, W is a vector subspace of R3. Fine. Okay. Now let us see one more example. Example 2. So with the usual operations, okay, V I am taking as P3 over R, that is polynomials of degree less than or equals to 3, okay, and W I am taking as P2 of R, that is polynomials of degree less than equals to 2. So clearly we can see that actually P2R is actually a subset of P3R, right? Because all the polynomials whose highest degree is 2 is actually contained in all those polynomials whose highest degree is 3. So is P2 of R a vector subspace of P3 of R? This is a question. Okay, so we saw in the previous example that we just started with, the example we saw here, the set of all polynomials, example 2 that we just discussed, we said that the set of all polynomials is actually a vector space. So here what we are taking is that I am taking a particular case of it. I am taking okay, that let me take V as set of all polynomials whose degree is less than equal to 3, W I am taking a set of all polynomial of degree less than equals to 2. So now is P2 of R is a vector subspace of P3 of R? This is the question. So first is very trivial that P2 of R is actually contained in P3 of R. So the first condition is actually fine. Now we have to check the three conditions, okay, to say or to claim that okay, P2 of R is actually a subspace of P3 of R. So any member of P2 of R has the form. So what is the standard form of any 2-degree polynomial? It is a0 a1x plus a2x square, obviously. So clearly, if I take all this a0, a1, a2 as 0, I'll get 0, and that 0 belongs to my P2 of R. So the first condition is okay. The second condition is if P1 and P2 are in my R, P2 of R, P2 of R, okay, just P2 of R, what about their sum? So if my P1 has the form sum a0 a1x plus a2x square, P2 has some form b0 plus b1x plus b2x square. What about my P1 plus P2? Obviously it is nothing but a0 plus b0, a1 plus b1 and a2 plus b2 times x square. It means if I take any two polynomials of degree at most 2 and if I add them, I'll always get a polynomial of degree at most 2, which is fine. So the second condition is also satisfied. So this is also true, right? This belongs to my P2 of R. What about the third one? That if my P1 has some form a0 a1x plus a2x square, then what about alpha P1? Obviously it is also in a P2 of R only, because it is not going to change the order of the polynomial or the degree of the polynomial. Okay, this is again in my P2 of R. So the third point is also fine. So we can say that actually P2 of R is a subspace of P3 of R. And in general actually we can say, similarly we can actually show also that in general Pm of R is a subspace of Pn of R if m is less than or equals to n. So here we saw that actually, m was 2 and n was 3. So P2 of R was a subspace of P3 of R. So in general we can say it for any m and n, provided that m is actually less than or equals to n. Okay, so this is fine. Okay, so like I have a quick question. So the question is, let I'm taking V the set of all polynomials of degree exactly 2. Is this a vector subspace or a vector space? So can anyone make a guess? Will this be a vector space? Yeah, so I'm waiting for your response actually. So you guys have no idea? Fine. So the answer would be actually no. And the reason is that I'm taking one polynomial as x square. Okay, this is a 2-degree polynomial. I'm again taking a polynomial p2 of x as minus of x square. This is again a 2-degree polynomial. But if I add this p1 and p2, what I get? I get x square minus x square, that is 0, which is not a polynomial of degree 2, right? Because here what we have specified is that degree should be exactly 2. But in the previous example, we considered degree at most 2. So when we say at most 2, it means the degree can be 0, 1 or 2. But when we say the degree is exactly 2, then the degree has to be exactly 2, and this we can say that it is not closed with respect to addition, and hence it is not a vector space. Okay, then there are some more examples. Example 3, I would say. Okay, so I want to say, okay, so I should have actually said this before only. So any vector space V over F has at least two subspaces. Okay, one is the zero subspace. Zero subspace means you take the set W as the singleton element 0. So when you take the set W as the singleton element 0, then obviously it will satisfy all those properties because 0 is in W. Fine. If I add 0 to 0, I'll again get 0, so it is closed also. If I multiply anything with 0, I'll again get 0, so it is closed, and the scalar multiplication also. So this is also a vector space, and this is called the zero space. Okay. And the second trivial example would be when W is equals to V itself. Since V is a vector space, and we know that every set is a subset of itself, so I can take W to be V itself, and hence W is again going to be a vector space. So these two are actually called these two vector spaces are called improper or trivial vector spaces. So not vector spaces, actually vector subspaces. So these two are actually called improper, or we say that actually these are uh, trivial vector spaces, because this is going to be true for any vector space. Okay, so this is our improper or trivial vector subspace, and any vector space V which is not the zero subspace, or V itself is called the proper subspaces, proper vector subspace. So except these two, anything, any vector space, we call it as proper, and these two we call it as improper. Okay. So I'll give you one or two examples actually to work it out for yourself. So this is exercise that we saw that the set of real sequence forms a vector space today only. I gave you that example. So now I am giving you a particular example of that set. That is, you take all those sequences such that all those sequences converges to 0. Okay, converges to 0 means an tends to 0 as n tends to infinity. Okay, then W is a subspace of the vector space V, where V is what? The vector space of all sequences. So clearly you can see that all the elements of W are also sequences. So W is actually a subset of V. So all you have to show is that W also satisfies all these three properties that we just wrote. And one more example that I want you guys to actually try, that take V as R3, okay, and W you take as the simple set A. That is, all the elements are same. Then W is a vector subspace of R3. So these two examples you guys should try. Okay. Now, okay. So one thing I just want to tell you, that note, is R2 a subset of R3? Now, is it true? Yes or no? Can anyone tell me? Is R2 a subset of R3? It is a very basic question. Anyone? Okay. Yes. So the answer is no. Okay. R2 is not a subset of R3. Now why? See, for a subset, you need to have same elements, right? So elements of R2, they look like as this, A comma B. They are ordered tuples, while elements of R3 actually look like A, B and C. So all the elements in R3 has three components, A, B and C, and all the elements in R2 has two components, A, B. So R2 is actually not a subset of R3. Okay, this is an important observation, because many a times we get confused that R2 should be a vector subspace of R3, but it cannot be, because R2 is not even a subset of R3. Okay. Next, okay, so we'll stop here. We'll see what are the algebras of vector subspaces from the next class. So I'll just stop broadcasting. Yeah, so I'm going to flash the attendance, and I want actually you guys to mark your attendance. I'll just flash it in a minute. Yeah, so BSc 4th sem, the first one, I am going to generate, okay, and I want all of you to actually mark your attendance quickly. Yeah, so please mark your attendance, and if you have no doubts, then you can leave the meeting. Code expired, okay, I'll generate again. So is it done? Yeah, you can leave the meeting now, or if you have any question you can ask.